So now it's okay. So first of all, I would like to thank the organizer for inviting me to give a talk, and it is a very nicely organized conference. Okay, so this joint work with AL. So he is from France. So our interest is to study what are the morphisms from P2 so to GR24, that is this Grassmannian of two-dimensional quotients of C4. So I am always working over complex number. Okay. And this projective space. So before going to this thing, so I'll start with some motivation in the case of, look at mapping from P1 to P2. Okay. So this I want to generalize this situation to this situation. What are the possible generalization? What are the things one can say about the morphism? So for that, first I'll recollect what are the things known about morphism from P1 to P2. So if you have morphism from P1 to P2, if it is non-constant map, so you have OP21 here, you have phi here. So if you look at phi star of OP21, so this is a line bundle on P1, which is of degree some d. Okay, it will be like this. And so first of all, one knows that if d equal to 1 and 2, phi is an embedding. And if d is bigger than or equal to 3, then phi is not an embedding. But if it's not an embedding, but it's almost embedding in the sense that for a generic phi such that P1 to P2 such that phi star of OP21 is OP1 d greater than or equal to 3, phi is an immersion. In the sense that it's not only immersion and generically one-to-one. Okay, and for any d you can find such maps for any d greater than or equal to 3. So we wanted to understand what is the situation of P2 in Grassmannian. See, this is the projective space. This is P2, P1 is half dimension of this thing. So want to know what happens in this situation. This also, P2 is a half dimension of this. This dimension is 4. So we want to understand what are the possible maps from P2 to P2. So note that giving a morphism from any x to GR24 is equivalent to giving a vector bundle E on X, and also I will always assume all the varieties that I consider are X means projective varieties, smooth, not necessarily smooth, but always assume X vector bundle of rank 2 E on X and a surjection from O X4 to E. Okay. Because on GR, in definition, this is GR4, I can is set of all C4 to V such that this surjection dimension of V is 2. So this is the set of all two-dimensional quotients of this thing of C4. So then on this you have a vector bundle, what is called the Q, where Q is the universal quotient bundle, that is, you have a surjection like this, C4 tensor, I call this as G, G2 Q, you have a surjection. So given such a surjection, you can take, so this you can identify with C4 at a point, this is going to see X4 to the corresponding quotient, two-dimensional quotient. So you get a map like that. Conversely, if you have a morphism, you can pull back, you get a quotient like that, vector bundle like that. And once you have this, so note that kernel bundle of this map, yes, this of C4 to kernel of C4 OG to Q, so this I denote by S, is also rank 2 bundle. So hence we have an exact sequence 0 to S to C4 tensor OG to Q to 0. Okay. And so if look at, if you have a, if phi is a morphism from P2 to GR24, then we have phi star of P2, the class, this is a class in H4 of GR24, Z, with coefficient Z, but this is isomorphic to, it's actually equal to Z C2 of Q, there is some Z C2 of yes. Okay. So that means this determines an integer, two integers, A and B, in this, in terms of the generators. So in fact, what are these integers? In fact, one can show that this, yeah, A is nothing but, so you have, once you have this morphism, the second chain class of phi star of Q is A and B is second class of of phi star of S. Okay. So these are this belongs to H4 of P2 of Z. So this again I can identify with Z, but only thing is the square of the hyperplane class, that is a class of a point. So this both of them belongs here. So these two numbers determines this thing. So one can ask, given AB in H4 or G2 for Z, does there exist a morphism P22 GR24 such that this phi AB is determined by phi, meaning the phi star of P2 is AB. One can easily see that not all AB is represented by classes. So not like, unlike in the case of P1 to P2. So everything is represented, but here it has to satisfy the following condition. Huh? No, degree, it will come. So that's what I'm saying. So first of all, this question has negative answer in general, given this thing AB. So meaning AB has to satisfy some condition. That's what I'm going to write. Okay, so that is follows from the cohomology of the Grassmannian. So that is if M is equal to phi star of Q, then meaning M times H. So this is a class in H2 of P2 of Z. So H is the ample generator of this thing. So then you'll see that M squared should satisfy this A plus B. So it has to satisfy this condition. If whenever you have a morphism with this thing, with A and B given such that AB is represented by an image of a this thing, so then it has to satisfy this property. Because that in the cohomology ring of the Grassmannian, H squared is, meaning if I take the ample generator, H1 is the ample generator of H2 of GR24 Z. So then H1 is actually C1 of Q, okay, and it satisfies H1 squared is equal to C1 of C2 of Q plus C2 of S. So it satisfies this property. From that you can see that A and B has to satisfy this condition. Okay, and I think during 70s, the theorem of Tango H so for what possible A and B, this AB is the following. Yes. Yeah. Oh, sorry. P from P2 to GR24 is an embedding in only 3 cases. So the only cases allowed are either so phi star of C1 of phi star of Q is H, or C1 of phi star of Q is 2H. Only in these 2 cases you get embedding, and you can write down what are A, B in those 2 cases. And in the first case, it's the linear embedding of P2 in the Grassmannian, and in the second case, this is the Veronese embedding given by the quadrics. So these are the only 2 cases which is an embedding. Okay. And so the next question is, can given A, B, which satisfies these 2 conditions, does there exist a morphism from P2 to this thing? So this question was settled by recently, some 3-4 years back, by Philip Ilya. He proved that, meaning some under not all A, B, such that A plus B is M squared. Both A, B positive and non-negative, and this satisfies this condition, or represented by that. But and also he gives the full classification of all pairs A, B which satisfies that. We had with myself and Abdul Ghani and one more collaborator, Laitami, we had some partial results. So he completed this project, and he proved what are all the possibility in this thing. Okay, so next we wanted to see, so this answered the question about these 2 things, existence. So then we wanted to study what are the possible morphisms, what are the images of these surfaces. Okay. Yeah. So we don't know the general answer. So first we considered some special cases. So E is a vector bundle of rank 2 and on P2. So what we first we settled is in, so if 2-2 case, that means both the A and B are 2-2, then what we settled was, so this was with the this only. And myself. We showed that in this case, the only possible images are as follows. So image has to be contained in, so note that first, so once you have this GR24 is naturally sitting inside P5, okay, and if you have such a mapping given by these 2 things, then what happens is now the image of P has to be contained in GR24 intersection some hyperplane. Okay, so here also there are 2 possibilities. One can show that in any such morphism has 2 kind of property. One is its image is generically 1-to-1, but it has a singularity along a curve. Okay, so that is one. Actually, it's a complete intersection of two quadrics in the Grassmannian. One can show that. Okay. And similarly, the other cases, so you have this, if you take another, this thing, GR2, 4 intersection. So I'm using bad notation because this H is a hyperplane section, so I should have this thing, so I should not get confused. H intersection H prime. So both are hyperplanes in P phi. So intersection of this is a quadric in P3. So image quadric has to be a cone over a curve in P2. So, and the mapping is 1 to 1, sorry, 2 to 1, except on a curve which is ramified along that curve. And there is a point on which the mapping is actually the tangent space level mapping is 0. Okay? So that's where the singularity of the image, that is the cone, the vertex of the cone coming into picture. Okay? So next, this thing is natural bundle one has to consider. So this answered the case. So case for C1 of P star of Q is less than or equal to 2. So if we wanted to understand what happens to other cases, but the first natural example for C1 Q equal to 3 is the tangent bundle. So let P equal to tangent bundle of P2, then C1 of T of P2 is 3H and C2 of TP2 is 3H squared. So this is a class in, if I think of H2, P2 Z, and this is a class in H4, P2 Z. Here H square means the intersection of two hyperplanes, that's a point. Okay. So, and also one knows that this maybe T of P2 comes in the exact sequence like this, 0, what is called the Euler sequence, OP2, O of P2, 1, 3, T of P2, 0. And from this you will see that H naught of T of P2 is 8, and also it's known that TP2 is ample. In fact, if you take P of T of P2, then and take O of P1, and then it is embedded inside this thing, P of 7, using this OP, this thing. Okay? So gives an embedding. So from that you will see that the tangent bundle is generated by sections. So because it's generated by sections and ample, so the minimum number of sections which generate TP2 is 4, and one can show that there are 4 sections which generate that. So there exists mapping from P to 4, meaning O trivial bundle of rank 4 to P2 this thing, you have such a surjection, and you will have kernel rank. So we'll call this as E star, a rank 2 vector bundle. So the corresponding class of, so since because you can compute these things, the corresponding class will be 3, 6. Okay. So yeah, at least we didn't find anywhere in the literature what are the images, what are the possible images of such mapping given by this kind of surjections. So first of all, it was not clear to us whether there exists a morphism which is generically injective. Okay. So yeah. Okay. So what we proved is the following. So yeah, for a general choice of 4 sections giving this generating TP2, the corresponding morphism some P from P2 to GR to 4 is generically injective, and in fact and is an immersion. So in other words, the tangent space level, the mapping is injective. You can show such a. And by theorem of Tango, this is the best possible one can expect because it cannot be an embedding. Okay, so sorry. Yeah. So see, this generic choice of such a section corresponds to this thing is a general theorem. So for that, one has to produce one example for which this mapping is having this property, generically injective and is an immersion. So this is what we do in this thing. Once we do that, then it follows that you can, this theorem follows. So for that, what we have to look at this sequence 0 to O P2 this P2, the Euler sequence TP2. So this is given by this x, y, z. So where x, y, z these are the generators. It's a homogeneous polynomial of OP2 of 1. So this is a 3-dimensional vector space. Take the 3 generators x, y, z, and if you take them, then you will get a mapping from O1 to this 3 copies of this, and which is nowhere vanishing. So hence the tangent bundle is the quotient. Okay. So and if you look at, so to give 4 sections which generate this, so it's enough to give 4 sections here, along with that this vector they generate that. So that's what we do, and just write down this simple. So so if we take, so V0 is this x, y, Z, V1 equal to x0, 0, V2 equal to 0, y 0, V3 equal to y, z, x, V4 equal to z, x, y. Then we prove that the corresponding linear system, which is given by T2 to GR T4, which is contained in T5. The corresponding linear system given by these things is nothing but x, y, z going to x, y, z, x into z squared minus xy, x into xz minus y squared, y into x squared minus yz, and y into yx minus z squared, and the last one is 3xy z minus x cube plus y cube plus z cube. So this is the corresponding map one gets, and one can show that this is base point free and all those things, and in fact one can show that it's an immersion. And also if S1 equal to this set of these three vectors, namely 1 0 0 0 1 0 0 0 1, all these will map to 0 0 1, and S2, so this 1 1 1 and omega squared 1, omega squared omega 1, all these three maps to 1 0 0 0. Okay. So from this calculation one see that you have such a morphism which satisfies this. Then one can show that from generality that for a generic choice of thing it will be like this. Okay. So yeah, one consequence of this study is the following. So there exists, so there is a corollary, there exists a irreducible component H, component H of the Hilbert scheme of surfaces in GR 24 such that every member of H is a singular surface. So this H is actually the, look at this mapping that I have defined. Look at the component containing that image. And one can show that this in fact satisfies all these properties. Okay. Because what happens is, so this, look at this mapping given by this selection of these sections. So the image is a surface with two singularity, namely the images of these two, this point and this point will be a singular point in the Grassmannian, okay, and outside which it is non-singular. So if you take a hyperplane section, so it's actually given by, it's a smooth hyperelliptic curve of degree 9, okay. So, and there is a classification of surfaces of type 3, 6 in the Grassmannian by Mark Gross, and he says if you have a smooth surface in the Grassmannian which is represented by this class, then the genus has to be greater than or equal to 2. I think he gives he writes down exactly what are the possible genus, okay, and so genus 1 cannot be there in that case. So from that one can conclude that this, there is, look at the Hilbert's component containing this, so it has to be consists of only irreducible surfaces. Huh? Yeah, in this case I know the singularity. I think if I perturb a little bit, I can make it only 2 points going to this thing, but I think there will be some 3 pairs of 2 points which map to distinct this thing, 3 points. So you can make it that kind of singularity. I have not written it down, but one can make, I think. So I think that's all I wanted to say. So thank you. Huh? Huh. Is it? Yeah, I think this will have different. This is one single component, but there are other components. Yeah, of same this thing. Yeah. What surfaces? Reducible surface. Yeah, right. When you in the limit. Yeah, right. Yeah, but the general member is this kind of thing. Was it known earlier, this kind of examples? Okay. Okay, thank you. So I think being the last speaker, I should thank the organizers once again. I hope all of you join me in appreciating the organizers for their excellent job in completing this conference. Very nice conference.
So maybe a few words to thank all the people involved. The participants have been very considerate, and I enjoyed this. I probably enjoyed organizing this conference more than you all enjoyed attending it. So thanks for that. And thanks to the staff here at ICTS. Thanks to Mansi for her efficiency, and the School of Maths back at Tata for all the work that it did. It's been a pleasure working with them. And thanks to all my co-organizers. This was the idea of my colleagues in KIAS when I was a postdoc there. And it sort of snowballed into this big project to sessions of Ravi Rao, who was the then dean. I thank him for the great idea. And Ravi Rao has sent his regards to all of you and apologies that he could not make it. So thanks, and hope this was a nice step.